We're starting a new topic. All right. This is one of the most integral component of food analysis. Okay? Sampling and sample preparation. If we mess this up, throw away your data. Means nothing. So sampling and sample preparation, we'll deal with it throughout the semester. Practically, we'll deal with it in the lab. So I will introduce it today theoretically. Okay. Let's read this together and give me an answer. What makes sense to you? Michelle.
Letter C.
C. C is correct. Anything else stands out for you? Amanda. Amanda goes with all of the above. What were you going to say, Paige? Paige has it right. We're going to say B and C. Correct. The first one, it tells you that we're measuring the whole lot. What if you're producing 100 tons a day? Are we going to take all of the 100 tons and take them to the lab and assess the quality? We cannot do that. Okay, so often, most of the time, 99.9% of the time, and the analysis does not allow us to do this. There is a certain analysis that allows us to scan everything, like metal detection. All of your sample goes on the belt and get detection of metal. So it's obviously non-destructive, and all of your product goes through that assessment. So B and C is correct. For sample preparation, prior to analysis, the following is true. First of all, do you know what mesh size is, or mesh number? Have you heard this term? What is it, Holly? Do you remember?
Yeah, it's like the amount of openings that a sieve has in a square inch, so it measures particle size.
You are 99% correct. So it is the number of the square opening. There are usually squares opening in a linear inch. So it's not a square inch. So it's a linear inch. Okay. Just guess. And you might not know this, but guess. Do you think you should eliminate enzymatic activity? Paul?
I say A.
So you're only going for A. Okay. Anybody? Sam? You were going to say none of the above? Oh.
Maybe not.
William?
I say C.
What is it?
C. Like cat.
C? Like cat. Okay. All right. I'm looking for the correct answer as of now. Go for it, Anne. I'm still looking for the correct answer. What? No?
B and C.
Thank you. You guys, I'll get you later.
Sure.
Yes, it's B and C. Definitely, you don't want any enzymatic activity. You will change the nature of the sample. You will change the composition of the sample. So you don't want that to happen. You don't want lipid oxidation either. You're changing the flavor. You're changing the composition of fat. You are doing things to the sample that you don't want. Here, I know this one is tricky. You wouldn't know to what mesh number, but 20 is the regular mesh number. But for extractions, like fat extraction, you want to go with smaller particle size. So you go with higher mesh number. Higher mesh number is meaning smaller particle size. So you have more holes in one linear inch. That means your particle size will be smaller. So for fat extraction, for example, it's recommended to do 40 mesh size rather than 20. 20 is for moisture, protein content, moisture content, ash content. So you can grind your sample to that mesh size and it'll be okay. Okay, good. You didn't know that. It's okay. We had some entertainment here. So is it feasible to evaluate all foods or ingredients from a particular lot? We talked about it's not feasible, especially when we have that many, big number of samples or a large amount of production, unless it's a rapid method and non-destructive. So we are going through and doing metal detection throughout. So I hope it's continuing where we left off in terms of recording. All right, ladies and gentlemen, come back. Okay, so we do not necessarily measure the entire amount of sample that we have, the entire production. So 99.9% of the time you sample. That means you take samples to test from the population. That's what we call sampling. So you take samples out of your entire population and you want them to be representative of the entire population. That means when you do the measurements, you want to be confident to say the entire population is acceptable or the entire population is not acceptable. So the samples you select are representative of the population. So that means, this is what I was saying, accurate estimation. That means your representative samples should provide you an accurate estimation of the quality that you are assessing, based on which you make a decision. So what helps with the accuracy of estimation is the number of samples you pull out and how you select your samples. So what methods of sampling you get? Is it random sampling? So we'll talk about random sampling versus non-probability sampling and so on. So the sampling method and the number of samples you need to select so that you reduce variance and you have more accurate and affirmative conclusion that represent the entire population. So in order to do that in confidence, you start out with a sampling plan. So you lay out your sampling plan before you start testing. So if you are going to do the project, the first thing that I tell you to include for every step, ingredient, processing, and end product, is what is your sampling plan. So the sampling plan includes the sample size. And by sample size, I don't mean the weight of the sample or the volume of the sample. I mean how many samples you're going to pull out. That is your sample size. So you have to determine sample size. You have to determine sampling procedure. How I'm going to take out my samples, and I'll give you procedures in a minute here, the different procedures that we use. Sampling procedure, you're going to use statistics, random, non-random, or mechanical or humans that will go pull out samples. So what is the sampling procedures? And then there's the sample preparation. How are we going to prepare our samples to ensure accurate and low variance results? The sampling plan also includes storage plan and transportation plan. How are we going to store the samples? So you took the samples, prepared them for analysis, but you're not going to measure today. You spent the whole day sampling. You're going to measure tomorrow. So under what conditions am I going to store my samples? Do I need to preserve it from light? If I'm measuring certain vitamins, yes, I want to ensure that it is stored in the dark. For instance, am I worried about temperature, rise in temperature or rise in moisture? I want to make sure that it is sealed, flushed with nitrogen, potentially to reduce any oxidation. So how are we going to store the sample is very important, because the way you store the sample will impact your results. Transportation plan, if you pulled out samples, but your analytical lab is 30 miles from the plant, because you might have your R&D or analytical plan at different location. So how am I going to transport the sample? What containers I'm going to put it in? Maybe I need a refrigerated truck to take my samples, especially if I'm looking at micro, for instance. So storage and transportation is part of your sampling plan. So Factors that affect the choice of sampling plan, and here I put in red define. That means define your sampling plan. Or everything I just said 5 minutes ago is what's the definition of sampling plan, what does it include? So if I ask you in the test, what is your sample, what does a sampling plan mean, or what does it include, you want to make sure to talk about all of these points. So choosing a sampling plan, that means choosing the number of samples you need to pull out, where you're going to get your samples from, how you're going to measure them, how you're going to store them. All of this, you have to know certain things, like what is the purpose of the inspection? Are we looking to accept or reject a lot? That means, are we looking for something that might impact the safety of the consumer? Or are we just looking at a quality measure? Protein content, moisture content, color, or are we looking at something more serious, like would impact health, amount of pesticides, for example. So that determines how many samples, for example, you need to pull out. Nature of the product, is it homogeneous or heterogeneous? If we're looking at flour, it's homogeneous products, all flour. If we're looking at a more complex food product that has different components, it's heterogeneous, then we need to think about how do we want to homogenize it first before taking out a sample, or maybe taking out a sample from different locations if the product is not homogeneous, and so on. So this is table 5.1, page 64. It's good to look at and familiarize yourself with what factors, so if I ask you in the test, what factors impact your sampling plan, so you can select any of these factors and explain them a little bit. So nature of the test method, is the test critical or minor? That is the same example I told you, somebody going to get sick. Does it have mycotoxin contamination? Or is it just looking for quality? Is the test destructive? Or is it non-destructive? If it's destructive, we want to be careful for the amount of sample we want to pull out, because obviously you want as minimum amount of sample as possible, so you don't use a lot of samples from your actual population. So, and the nature of the population, how big it is, are the different lots consistent, are they small cans, you're producing small cans, or producing boxes, or you're producing flour in bulk. Okay, two last things before I let you go is the difference between attribute sampling and variable sampling. So attribute sampling is for randomly distributed attributes. That means attributes that are not homogeneously distributed throughout your product. So microbial contamination or fungal growth or mycotoxin. They might be located in certain parts of the food, not in all of it. So you need to, in this case, have a large sample size. That means you need to take a lot of different samples from the population to ensure that you screen all of the possible locations. So that means here in this case, an example is to check the presence or absence of a variable and then decide acceptability. Example could be Clostridium botulinum in canned goods. Is it there or not there? If it's there, you reject it. So organism of concern, you measure presence or absence. You get, if it's present, you get two classes. So either if it's present, there is zero tolerance, that means more than zero, you reject. So if there is any, it goes to reject. Count is zero. No more than zero count. If there is a different organism or a different component of concern, like a residue that is of concern, like a pesticide, what would be the concentration? If it is within the allowable concentration, you accept. If it's over the allowable concentration, then you would reject. one minute, and then we're leaving. Variable sampling, this is for normally distributed attributes. So those are the attributes that are equally distributed in your sample. For example, moisture, or ash, or fat, or protein. They're present equally wherever you take a sample. They will be in the same concentration if you homogenized your sample. So in this case, you don't need large amount of sample or large number of samples to pull out. Just a small number of samples to pull out because the attribute is normally distributed. And it's mostly for quantitative analysis, where you are looking for concentrations or quantity on a continuous scale, and then you decide acceptability based on the quality specifications that you have compared to an acceptable value. So color, total solids, salt, protein, moisture, fat, all of that. Okay, I'll let you go. Let's pick up where we left off. All right. So some recap questions. Those in gray, we haven't gotten through them yet. Look at them later when we're done. Define a sampling plan. Who would like to define what sampling plan means or entails? As much of it as you can remember. You don't have to have the complete answer. Sammy. So everything that Sammy listed, which we probably could not hear, all of it, I'm going to go back. Where is it? Where do I have it? Did I just pass it? Okay, sampling. So sample size, meaning how many samples we need to collect to be representative of the whole lot. What kind of sampling procedure we need to use to collect these samples. How are we going to prepare them and preserve them until analysis so that we don't change composition or characteristics of the sample, as well as during transportation. So if the samples are being prepared, pulled from one plant and then going to be analyzed in your laboratory somewhere else, how they should be transported so that we don't get differences in the composition. Okay. Why is sampling plan important? Laura?
If you don't have a good sample, you don't have a good plan, and all your data is going to be accurate.
Exactly. So basically, it's the most important integral part of the entire process of food analysis, because if we mess it up from there, from the beginning, we cannot trust any of our data. So we have to do it right, so whatever we analyze, we can trust and make good decisions. What is attribute sampling? Michelle?
Attribute, it's checking for presence or absence of a variable to determine if it's acceptable.
Yes, checking of specific component that is not randomly distributed, or that is randomly distributed, not normally distributed. That means it can be in any location in the food. So it's not homogeneously distributed in your food. Whereas variable sampling, William?
It's normally distributed, and usually there, you're looking for
So it's normally distributed, it's there, so you take a small set of samples to determine that variable attribute. Okay. So the size, that means how many samples we put out, or how many sets of samples we put out, is really dependent on our purpose. What do we want to look at overall quality? What would be sampling cost? What is the objective of the analysis? So many different variables. But if we are doing analysis for certain component that is regulated by the government, like nutrition labeling, we have to follow the way they wanted us to do it. So the specific sample size is dictated by that agency. So for example, the FDA and FSIS for nutrition labeling require composite sampling. And I'll talk about this later, but composite sampling, it means that they require you pull out 12 samples randomly from your population, at least 12 samples, and you combine them, hence the composite sampling. So you combine them, and then from there you take 6 replications. So this is required by these agencies. Okay, so in order to accept a lot or reject a certain lot, so you go by obviously sampling, and there are different sampling sizes. So you go with single sampling plan. That means you take one set of samples from your population. That means N is for the number of samples you pull out, and C is for the number of units that are defective. So how many samples are defective? So based on what is allowable, so maybe you're allowed to have 5 defects in the samples that you pull out, then if they are less than 5 defects, then you accept. If they're more, then you reject. Double sampling, that means you take 2 sets of samples, set 1 and set 2, and then you look at number of defects, and then you determine, based on the number of defects in the 2 sets of samples, you determine whether to accept or reject. Multiple is an extension of double, so you take multiple sets of samples, and then based on the number of defects, you accept or reject. So the complexity, or whether you decide for single, double, or multiple, it depends on the risk of accepting a lot versus the risk of rejecting a lot. And that I'll talk about later, because you don't want to risk accepting a lot, for example, that has health consequences, that you really want to be very careful in doing multiple sampling or even sequential sampling. I'll talk about. If it's just a matter of consistency and quality, and you are really being consistent, and it's not something that you're going to risk the health of the consumer, you might going to say, okay, single set of sampling, if it passed, then we're all good. So sequential sampling is an extension of multiple sampling, and it is in a sense that you take a set of samples. Let's say you take a set of samples with 40 individual sample that you pull out, like 40 cans, for example, from the lot. And then you look at certain defects in the can. Let's say we're looking at a particular defect. If there is a hole in the container, there's oxygen that went in or something like that. So if you have 40 samples and you found 1 or 2 defective samples, you just accept and stop sampling. But if you pulled out, let's say 30 samples and you found 8 defects, you just reject. If you take 20 samples and you found 2 defects, you continue sampling. So it is a more extensive type of sampling, but again, it really depends on the risk for accepting or risk of rejecting your sample. So here's an illustration. If it says, so you have your population, you take out a set of sample. If it is below a certain defect number, you accept it right away. If it's above a number that you stated that this is the maximum defects we can have, you reject right away. If it's in between, you take another sample and again test the defects, and then count the defects, add them up, and compare them to a minimum accepted and a maximum accepted.
I have a question.
Yeah, of course.
I think I understood on the previous slide when
On the previous slide?
yes, the middle part, the if, when do they take a second sample?
So the if the number of defects is between an acceptable and the maximum acceptable. So if it's in the middle range, then you take another set of samples. So in case of looking at mycotoxins specifically, which one of these is correct? Remember, participation was worth 2 points. So if you know the answer, or you think you know the answer, don't hesitate. Even if it's wrong, that's fine. Okay? A and C. And?
I'm going to say A and C.
Amanda? A is correct, C is correct. So A and C. So because mycotoxin is an attribute that is not normally distributed, so you might have fungal growth on certain area of the food or in the lot, so it won't be distributed equally or normally within your sample. So you want to make sure you take out a lot of samples to ensure that you don't have mycotoxins. Obviously, it's not single sampling then, because if you take one set of samples and you don't find mycotoxins, it doesn't mean that mycotoxin is not available somewhere else or present somewhere else. And if you make an error, a sampling error, the impact of an error in sampling is much greater than the impact of your analytical error. And again, if you sample incorrectly, you might make a decision that could be harmful for the consumer, or may cost you, if there is no mycotoxin, might cost you a lot of money to reject.
We were talking about like the acceptance sampling. Will it usually be referred to as like single acceptance sampling plan, or will it be like single sampling plan?
Say that again.
So we were talking about the acceptance sampling and
Yeah.
like single, double,
Yeah.
and all that. So will it, when it's talking about that kind of plan, will it be like single acceptance sampling plan? Because I guess I read B and I thought like a sampling plan is the big overarching
A single single acceptance sampling plan. Yeah.
Okay. So
Oh, that, yeah, I see where you're confused. I should have said single acceptance. So that,
it'll normally be written with acceptance.
yes,
Okay.
unless I mess up. So you can ask me like you just did. Okay. Yes, Anna?
What would be like an example of a single acceptance
Yeah, there are so many different situations where you have that. But let's say you're looking at a quality parameter that does not endanger your or have a high risk, and you know that you've been consistent in it for many weeks. Let's say you're looking for total solid content, okay? And then you just measure it, and you know that you've been consistent. There's no high risk in making a wrong decision. Yeah. Any other questions? Yes, yes, Sam. Say that again.
Would you be able to choose like a different sampling plan for like key components?
Yes, that's a very good question. Depending on what we're analyzing, whether we're analyzing mycotoxins in the same sample or we're analyzing moisture content of the same sample, sampling plan will be different. Yes. Okay, so the risks, here's where we have to think about the risk when we actually plan our sampling, whether size or the entire plan. We have what is known as consumer risk. That means this is really important because it impacts the consumer, whether from a health perspective or whether they're going to like your product and come back and buy it, or then you would lose your consumers or lose your customer. So, but most importantly, it's related to health. You do not want to accept a product or a lot that might have high implications on the consumer. So when you make a decision, you want to make sure that the consumer risk is less than 5%. Less than 5% of you accepting a poor quality population. There's also the vendor risk, because also you don't want to reject a lot that is potentially good quality and you just rejected it, because that causes you cost. It costs you money. You lose money that way. So there is always also that risk, but it is higher. There is more leeway to that, 5% to 10% of the lots. Overall, you want to be reasonable in your sampling plan. You want to think about time, efficiency, cost, all of that. So you want to make it as simple and as flexible as possible when you make your decisions. You want to protect both the consumers and the vendor, and you want to ensure that your results are true, are reliable, you can trust them. So this is an example of sampling procedure. So within the sampling plan, after size, we think about, okay, we determined how many samples we're going to pick out. Now, how do we pull out these samples? This is a simple example of flour sampling. This is an official method for sampling flour from AOAC. In this case, let's say you are a flour mill and you're producing bags and bags of flour, and you want to test certain quality of that flour. So how are we going to do it? You're producing, let's say, in simple terms, 100 sacks of 50 pounds flour, but you're producing much more than that. If you're producing 100 sacks or big 50 pounds of flour bag, you take the square root of that number, which would be 10 in this case, and then you take samples from 10 bags randomly instead of measuring everything. So from these 10 bags, the way you pull out sample, you pull out 2 samples potentially from the throwing sample from the corner diagonal to the center. So if this is the center, so you go to this corner, or this corner, or this corner, or this corner. And you draw a second sample from another corner. You take these samples and you store them properly under in a sealed container in dry and clean conditions. So when you have a homogeneous sample, like a homogenized or mixed or stirred oil, so it's a homogeneous sample. So wherever you pull your sample of oil, it's going to be fine. It can be taken from any location. But sometimes you have a heterogeneous sample product. So let's say a truck full load of potatoes. Each potato is different. One might have mold on it, another might not have mold on it. So you really want to look at taking from multiple locations from that truck that is full of potatoes. So you have manual sampling, which is prone to human error. Usually it's done by experienced personnel, and you can use different tools to take out samples. This is an example of a core sampler. And you can have mechanical sampling, which is less biased, and it is for, let's say, in line of processing. You want to take a milk sample. So it would be, there would be a mechanical installation of a unit that would, after a certain number of minutes or hours, a sample is pulled for analysis to look at fat content after producing what you think is low-fat milk. So you want to make sure that you defatted the milk and you produce a 2% milk. So you, at certain time points, you would pick up the sample and do an IR on it to determine the fat content.
Is that
Carrie.
Yes. In that case where manual sampling will be preferred over mechanical sampling?
Yeah, mechanical sampling is not always feasible and present in your facility. Then you would have an experienced personnel online that would, not necessarily online too, it could be after production, so you would have to have a personnel that knows what they're doing when they're doing the sampling. So there are two types of sampling, non-probability sampling and probability sampling. Probability sampling is obviously preferred, but when you have situations where you cannot do probability sampling, such as when you have a container full of grains, so you really don't have the option to be able to randomly select samples, statistically select samples. So you rely on judgment sampling by an experienced personnel that would know where and how to take a sample. It is biased, obviously, based on the person. Sometimes it's restricted sampling, so you have this huge silo and you can only reach the top. You cannot really get a sample from the bottom. So that is, this is what you have and this is what you take. But many times you're able to do probability sampling when you are producing products such as canned food or individually packaged products, bags, packages, cans. So you are able to do probability sampling. In this case, you follow something we call random sampling. That means if you are producing a huge number of cans, obviously, an example, a lot of cans per lot, and of course you want to select a certain number of cans, let's say for nutrition labeling, so you're going to do 12 cans from this lot. So how do you select these 12 cans is by random sampling. So you get a random table of numbers, you number your cans, and then you select randomly, close your eyes and pick a number, 12 different samples, 12 different numbers. So that would be a randomly selected set of samples to be analyzed. Okay. Systematic sampling, that is similar to when you have a mechanical sampling online. Every an hour, every 2 hours, the sample is automatically withdrawn for analysis. That is systematic sampling, no human bias. It just goes by timing when a sample is pulled for analysis. Stratified sampling, this applies to if it's a company and they have multiple plants. So a company is producing tomato soup, tomato paste, or what have you. So, and they need to test their production for consistent quality across different plants. So each plant will be, you would stratify, so you would divide your population based on the number of plants you have, and from each plant you apply random sampling for each plant. So random sampling is within stratified sampling, and this is for when you have multiple plants producing the same thing by the same company. Cluster sampling is similar to stratified, so you stratify, you divide your population across the different plants. But in this case, instead of sampling from each plant, you randomly select which plants to test. And each time you select different plants. The composite sampling is the example I gave you for the government regulation, FDA and FSIS, for nutrition labeling, where you take 12 samples randomly from your lot, and you combine them, mix them well, homogenize them well, and from there you take 6 subsamples for analysis, or 6 replications. Which of these do you consider as potential problems associated with sampling that will result in reduced Jason? Yeah, yes, all of the above. Definitely, whenever you don't have a statistical way of picking up samples, you have due to convenience or restricted access, yes, this will be associated with reliability issues. For storage conditions, it's going to impact the composition of your sample. And yes, flavoring, obviously, that's a big blunder. So consideration when you prepare your samples. So now you have selected the number of samples, you have selected the way you're going to sample them, now you have to prepare them for analysis. So you want to have as much of a surface area as possible to enhance the accuracy of your determination. So oftentimes you have to reduce the particle size of your sample. So this is an example I give every year. I walked in one time on a capstone group trying to determine fat content in a potato chips. So they were doing that by using a Muginer assay, where there is a digestion tube and you put your sample usually, and then you put your, after the sample is digested, you just put it in there. I don't think they even digested the sample now that I think about it. And then you mix it with solvent to extract the fat. And I walked in and I found a whole potato chip in that flask. Like, what are you doing? Extracting fat? No, you're not extracting fat. You did not reduce the sample size or the particle size to allow for efficient extraction of the oil. So you really need to reduce your particle size. And often there is a recommendation for the size of the particles. So if you're doing general approximate analysis, 20 mesh, and we talked about that last time. Mesh number is the number of openings or square openings per linear inch. And then the higher the number, meaning you have more opening, meaning you get smaller particle size. And usually they recommend a smaller particle size when doing the extraction assays, because you want to increase the surface area as much as possible. Now there are cautions when you want to grind your sample and make it homogeneous. Sometimes your sample is moist or it's sticky or something that does not allow regular dry grinding that we use. You put your sample in your grinder and you grind it. But if you have high moisture, sticky, high fat, it's not going to work well for you, especially that because then you lose moisture, or moisture will prevent it from being homogeneously ground. And if you have fat, you lose some of the fat, will stick on the sides. So you cannot do regular grinding. So the solution would be cryo-grinding. That means you freeze your sample. You can freeze it with nitrogen, or you can put it in the freezer. Or you can freeze it with CO2, right, Cindy? The dry ice. Liquid nitrogen. We don't do it with dry ice? Yeah. Okay. Pour liquid nitrogen on top of it, and then it freezes and becomes solid. And then yeah. Oh, and sometimes we use it. I remember now. If you freeze it with liquid nitrogen in the grinder, you can put a couple of pieces of dry ice to keep it solid throughout the grinding process too. And who doesn't know what dry ice is? Huh? What is dry ice? It's okay if you don't know, if you haven't heard it before. It's not a very common thing. Well, it's common for us, but what is dry ice? Say that again. The solid version of CO2. Well, how do you make CO2 solid? What do you do usually for gas to become solid? Compress it. So we do a lot of pressure, right? To compress and make it, you can make CO2 into liquid, and you can make CO2 into, so you change the temperature and you change the pressure to bring that gas into a solid phase. Okay, just explain everything there. So while we're preparing the sample, other than, one other thing I forgot to mention is we always have to also be careful when we are grinding your sample is not to overheat. Some grinders can heat up a little bit, and heating up your sample can result in losing moisture, for instance, or initiating reactions that you don't want, side reactions that you don't want with high heat. So we have, sometimes we tell the student, okay, let it grind for a minute, stop, wait, and let it grind again. Another issue is metal contamination. So depending on the grinder you're using, where you put your samples in, especially if you're measuring ash or iron content or what have you, you don't want contamination from other material that you use. And then once you grind your sample, you filter the sample or run it through sieves that you can ensure these mesh numbers are reached. And there are certain ways you can do physical, using a sieve physically, and you put your sample on and just shake your sample through. Or there are tools like the rototap that has different compartments with different sieve numbers, and then you can utilize that to separate particles based on their particle size. All right, the last thing here, during sample preparation or storage, we want to eliminate enzyme or control enzymatic reaction. We talked about that as of why. Why we want to ensure no enzymatic reactions? Said that earlier. Yes, Hayden?
So that it doesn't change the product.
Yes, so it doesn't change our product. So you don't change the fat content by breaking the fats into different components and then they get oxidized, or breaking the proteins up, or hydrolyzing anything you don't want it to be hydrolyzed. How do we control it though? Sam?
Control, you stop the enzymes from.
Yeah, how do you stop the enzyme?
Freeze them, keep them very.
Yes, so you can store your sample. If you know that your sample is high in enzyme, store it under cool condition. You can freeze it, you stop the reaction with enzyme. Or you can begin.
The enzyme is sensitive to pH.
Yes.
Your product can endure the heat and the acid.
Yes, definitely. So you can change the pH if the pH is not going to impact anything else. If you can reduce the pH to an acidic pH, for instance, some enzyme will be inhibited. Were you going to say something? Sammy?
It's maybe some question, but if you were gonna test it on the shelf life, wouldn't you want local enzyme activity to happen with your product?
That is not a dumb question. That is an excellent question. Yes. So if you are measuring shelf life, you don't want to inhibit anything, because your mode of failure could be very well your lipase activity or like oxygenase activity. So you definitely don't want to do that. That is an excellent question. Good. Another way to eliminate enzymes, if you want to eliminate the enzyme, is by heat. You can denature the enzyme if whatever you're going to test is not impacted by change in heat or temperature. We want to avoid lipid oxidation, obviously, because this is going to change the characteristics. How do we avoid lipid oxidation? Paul? Yes, we can add antioxidants. Excellent. What other thing we can do that is very simple? Yes, Tia? Put it in a vacuum, yes. Put it in a vacuum or flush with nitrogen so that you can remove the oxygen and the nitrogen replaces the oxygen in your head space of your storage container. Very good. Antioxidant, flush with nitrogen under vacuum. Seal it well, put it away from light if you are worried about photooxidation. Limit microbial growth. Why do we want to limit microbial growth? Adele? Yes, well, spoilage, but what would spoilage do? Change the composition. Your microbes are going to ferment and eat up some of your constituents. You don't want that. Change the pH, change the sugar into acids. It's going to just mess up things for you. Okay, how do we control microbial growth? What? Controlling the temperature of storage, right? So we can store it in refrigerator or freezer. What else can we do? Sam?
Proper sealing.
Proper sealing, Bagheera?
And control the water moisture.
control water moisture. What else? But sometimes the water moisture is present in your food. You can't do much about it. Oh. What's that? Yeah, you can control pH level. Another thing I was looking for is you can add chemical preservatives to prevent the growth of microorganisms. So any measure you want to avoid alteration of your sample. Yes, Adam. Other microbes? You don't want to add any microbes because microbes will ferment, will grow, so they will be eating on something. And then who will live? Somebody's going to live. It's the life for the fittest, or whatever is that quote. Somebody's going to be fit and will grow. And how they grow is they're going to eat up your food. Good though. All right, so here's an extra credit option. So what you have here is this question comes from your study question for chapter 5. If you solve it and bring it to me on Monday, you'll get +5, not +2. So if you want that +5, which will come in really handy on your quiz and test, go ahead and solve that problem. Okay, I have 13 minutes to start a new lecture. What? What did you say? What? Oh! A for effort. A for effort. If you put effort, but it's wrong, you'll get the credit. If you put one sentence and no effort, yeah, you'll get a 0.